Okay, let's take a look at a reaction that we've done in the lab a few times. So this is the reaction of zinc metal with hydrochloric acid. And when we discussed this earlier, we said that we could think of it as the replacement of hydrogen by zinc, so that on this side we get zinc chloride and hydrogen gas, and then to balance we would have it this way. If we think about it a little differently, though, in terms of what's happening with electrons and the charge on the atoms, we notice that zinc is uncombined on this side, so it's neutral, and on the right side it will have lost a couple of electrons because it has a +2 charge, and the way something gains a charge is by either losing or gaining electrons. Right? The hydrogen on this side is +1, and on this side it's 0. Okay, so we can see that another way of thinking about this reaction is in terms of the electrons that are being transferred. So let's look at the zinc and just write what happens with zinc to begin with. So zinc starts off neutral, and it loses 2 electrons and gets a 2+ charge. And then here are the 2 electrons. And I guess another thing that you might pay attention to is that the charges also balance from one side of the equation to the other. Okay, if we look at the hydrogen on the left side is +1, and the hydrogen gains 2 electrons, so that on the right side it's 0. Okay, so the type of reaction where something gains in positive charge, or to say the same thing a little bit differently, loses electrons, we refer to that as an oxidation. And it's oxidation because it was originally applied to oxygen, but it extends to a lot of different elements. And then on the second equation, what we have is something that is decreasing in oxidation number, gaining electrons, and that's called reduction. And you also will notice that you're always going to have both of these reactions taking place. You can't have oxidation without reduction because the electrons have to come from somewhere. So usually these kinds of reactions are referred to together for short as redox, which is short for oxidation reduction. Alright, so one of the things that is useful, in fact necessary, in order to identify oxidation reduction reactions is to assign these numbers, which I have referred to as charge in the past, but in this case we'll start calling these oxidation numbers, and we'll look just briefly at the rules of how you assign those numbers, and then we will apply the rules to a few examples. It may be a little overwhelming to look at all these rules at one time because it seems quite complex and detailed, but in practice it turns out to be fairly easy to apply these rules. So I'll just mention them briefly right now. They're in your textbook and they're described in some detail there, and instead of going through the rules I will go through some examples and show you how they're applied. But a few of the most important rules are that the oxidation number of an element is 0, and that includes diatomic elements or substances like P4. So anything by itself is 0. If you have an ion with a charge, its oxidation number is the charge number. So if you have the chloride ion, which is -1, its oxidation number is -1. And there are certain elements that always have the same oxidation number when they're combined. So all of the group 1 elements are +1, all the group 2 elements are +2, fluorine is always -1, hydrogen is always 1 unless it's combined with a metal. So over here, like with sodium hydride, it would be -1. The other thing is if you have a compound, then you will know that if there's no charge on the compound, then the sum of the oxidation numbers has to equal 0, and that's covered in this rule. And if you have a polyatomic ion, then the sum of the oxidation numbers has to equal the charge on the ion. Contrary to what you might think by looking at these examples, oxygen is almost always -2. The only cases where it wouldn't be is if it's in a compound with group 1, like this one. And here you would actually use the rule for sodium always being +1. So if sodium is +1, that means each oxygen has to be -1. And then this is a little bit of an unusual example, but it is possible here for oxygen in some cases to be -1/2. Alright, so let's apply these rules and see how they work out in actual examples. Okay, for the first one, we have nitrogen in 2, and we said that anything that is uncombined, including the diatomics, is going to be 0, so the nitrogen is 0. We have N3-, and the rule that applies here is that the oxidation number is the same as the charge on the atom, so this is a -3. For the next one, for nitrate, we have to do a little work. So we know that the compound is like so. So the overall charge is -1. And we know that the sum of the oxidation numbers has to equal -1. So if we have oxygen, which is -2, and we have 3 of those, so we're saying what is nitrogen's charge when you add it to a total of -6, so that you get -1, and that would be +5. For the next one, barium oxide, barium is going to be +2, because it's in the second column, and oxygen is going to be -2. And then for the last example, this is one of the cases where oxygen can be something other than -2. So what we would say here is that the potassium takes precedence, so it's +1 2 times. And so if we have 2 oxygens, and we know that the overall charge has to equal 0, then each oxygen has to be -1. Alright, so these are just the basic rules, and we'll apply them and you'll become used to assigning them. It's really not quite as hard as it looks when you look at the list of the rules for assigning oxidation numbers. Okay, so this is a good example of how we can use the rules and also figure out what the term oxidizing and reducing agents means. So let's just go through and assign the oxidation numbers. So for chromium, the charge is 3+, so the oxidation number is +3. For H2O2, the oxygen in this case is going to be -1. For H2O, the oxygen is going to be -2. And for the dichromate ion, let me put this down here. So you have Cr2O7 2-. So oxygen is going to be -2 7 times. And here we're going to have chromium. And we have 2 chromiums, and the chromiums have to add up to a total of 12, so that you end up, by the time you add that charge to the oxidation number of oxygen, that you get a 2-. So the chromium will need to be 6. Okay, so I'll just put that 6 up here. Alright, so let's talk about these terms. Oxidizing, reducing, oxidizing agent, reducing agent. So first of all, we can look at what's happening with chromium. Chromium is going from +3 to +6. We said when something increases in oxidation number, it's being oxidized. So chromium is being oxidized. So chromium 3+ is being oxidized. And what's being reduced? So the oxygen goes from -1 to -2, so it's decreasing. So the oxygen, actually you don't have to say the charge on this, you can just say oxygen is being reduced. Okay, so then next we have 2 new terms. What's the oxidizing agent and reducing agent? So the simplest way, I think, to remember this is the substance that is being oxidized is reducing the other substance. So chromium is being oxidized. It means it's losing electrons, and where are those electrons going? Well, they're going to the oxygen. Okay, so chromium is being oxidized, but it is the reducing agent. So chromium 3 plus is the reducing agent. And if you look at it from the point of view of the oxygen is going from -1 to -2, so it's taking electrons away from the chromium, so it's causing the chromium to be oxidized. So we can say that the oxygen is being reduced, but for the reducing agent we usually say the whole compound that it's in, so we'll say H2O2. Alright, so we'll practice a few more of those, but that's kind of the basic idea there. Okay, and finally we have a stoichiometry type problem that can of course be applied to an oxidation reduction reaction. This is one of the most common oxidation reduction reactions, and it's one that we'll do in the lab, so it'll be good practice to go ahead and look at it ahead of time. So we see that we have the same components in the problem that we had in previous problems. We have information about the volume and the molarity of one substance, that would be the iron nitrate, and about the other substance, which is the KMnO4, we know only one thing. We only know the molarity. So we can use this information plus the information provided in the balanced equation in order to calculate what volume of the KMnO4 that we'll need. So we'll do that next. Okay, let's start with the volume of the iron 2 nitrate. So over here I will first write 0.0275 liters, and I change the milliliters to liters. And next I will put down the molarity of the iron nitrate. So 0.250 moles of iron 2 nitrate per liter. Okay, so if I multiply those two, that would give me moles of iron 2 nitrate. For every mole of iron 2 nitrate, there is 1 mole of the iron 2 plus ion. Okay, and you'll see how that is going to matter to us in a second. Now I have to go down here, so I have to kind of extend this over. For the relationship between the iron 2 plus and the MnO4, we see that there are 5 moles of Fe2 plus that will react with every 1 mole of MnO4 minus, and for every 1 mole of MnO4 minus, we have 1 mole of KMnO4. Then finally, we can take into account the molarity of the KMnO4, so it is 0.684 moles of KMnO4, which I've kind of run out of room, per liter of KMnO4. So when I multiply all of this, I will get the answer, so I'll just pause for a second and do that. Alright, when I multiply through, I get 2.02 milliliters. And there would be another step where I would have to change liters to milliliters, which I didn't include, but you can easily do. Alright, so again, this has the same parts to it as the other problems that we've done. The only thing that's a little different is that the equation itself is a little bit more complicated. For this course, you don't have to balance these more complicated redox reactions, so all you need to be able to do is say what's oxidized, what's reduced, what the oxidizing agent is, what the reducing agent is, and then make a calculation